In this video, we're going to cover section 1.5.3, second order reactions, type 1. Let's consider the following elementary reaction step, where a single reactant species A is involved in the formation of a product P. Note that we have two molecules of A reacting to give us this product P. So if the reaction is second order with respect to A, the corresponding rate law expression is as follows. The overall rate of the reaction, epsilon, will be equal to K1 multiplied by the concentration of A to the square. Now, the reaction can also be written in terms of the time derivative of A. And note, because of the stoichiometric coefficient 2, that the rate of the reaction with respect to A is equal to minus, it's being consumed, 1/2 dA dt. Therefore, this differential rate expression relates the time derivative of A to the rate constant and the reactant concentration, and the quantity 2K1 is written as an effective rate constant, denoted as K effective. Now, this differential equation is also a standard differential equation that can be integrated as follows. So again, we're going to multiply both sides by dt and divide both sides by the concentration of A to the square, and then integrate both sides with their respective limits, A0 to A on the left-hand side and 0 to sometime t on the right-hand side. This takes the form of the integral dx over x squared, and the solution to that is equal to minus 1 over x. And so we end up with the following integration. We have minus 1 over A plus 1 over the initial concentration of A equal to minus K effective T. And we can rearrange that slightly to remove some of those negative signs to result in our final integrated rate law expression for a second order reaction type 1 of 1 over the concentration of A is equal to 1 over the initial concentration of A plus K effective times time. So for a second order reaction, type 1, the concentration of A will undergo what's called a bi-exponential decay with time. Although the initial decay of a second order reaction may be rapid, the reactant concentration will approach 0 more slowly than in a first order reaction with the same initial rate. So what's shown in this particular figure is comparing two bi-exponential decays with two exponential decays that we saw previously, where the magnitude of K large is 3 times larger than the magnitude of K small. And what you'll notice, especially with the K large set, is that for a first order reaction, we see an exponential decay that does approach 0 relatively more quickly than what we would observe with a bi-exponential decay. Although initially the rates are both decaying quite quickly, it's at longer times that we see a much slower decay of the concentration of A with time. And so that's a distinguishing feature of second order reactions compared to first order reactions, is that there is this exponential decay, but with a second order reaction, the initial decay is similar to a first order reaction in some respects, in that they're both rapid, but at longer times you see a much slower decay in the concentration of the reactant, such that it takes a significant amount of time to reach a concentration of 0. So for a second order reaction involving a single species, and that is the type 1, a good linear fit to the experimental data will be observed for a plot of the inverse of the concentration of A against time if there is a strong association between these two variables. And the slope of the linear fit corresponds to K effective, and the y-intercept corresponds to the inverse of 1 over the initial concentration of A. And as we've said previously, for both zeroth and first order reactions, it's important to note that the comparison of experimental data to an integrated rate law expression requires the variation in concentration with time be accurately known over a wide range of reaction times to determine if the reaction indeed follows a certain order dependence. And again, this caveat is important to remind us that we must collect enough data, a significant amount of data, to really observe the dependence that we are modeling. Now, like we've seen previously, we can also solve for the product concentration if we carry out this mass balance expression, if you will. So the assumption is always that if we have only the reactant present at T equals 0, then the sum of the reactant and product concentrations must equal the initial concentration of A. And so again, we rearrange for the product concentration, and we can substitute in for the concentration of A with the integrated rate law. Now what we obtain is a little bit more complicated quotient than what we've seen previously, but nonetheless, it shows that the product concentration can be determined at any time t, so long as we know the initial concentration and we know what K effective is. And finally, we can also calculate the half-life for a second order reaction type 1 in a similar manner that we saw for zeroth and first order reactions. So if we start with our integrated rate law for second order reaction type 1, single species, and we substitute in for the concentration of A with 1/2 A naught, we end up with the following expression, where we've also included the subscript for our time variable as T1/2 represents the half-life. In doing so, in carrying out a bit of a rearrangement, we end up with the following expression, where the half-life of this reaction is equal to 1 over K effective times the initial concentration of A. So in summary, for a second order reaction involving a single species, the half-life is dependent upon the initial reactant concentration and the rate constant of the reaction. This concentration dependence is expected given a second order reaction involves a bimolecular process. It involves 2 molecules. And so we would expect that when we have a high concentration of the reactant, that the half-life will be quite small, meaning we have that sharp initial decrease early on in the reaction. However, as the concentration of that reactant decreases, that's going to slow that half-life. And we saw that previously in the figures showing that by exponential decay, that we saw initially a fairly rapid decay in the reactant concentration, but at longer times it tended to not level out, but the exponential decay was much slower. So if you have any questions about type 1 second order reactions, by all means, send me an email. Thank you.